Building a Rubik's Cube manually is a lesson in repetition. You duplicate a block 26 times, align them by hand, and then manage dozens of separate materials. One mistake in the outliner requires a full restart. But in a procedural workflow, those 27 objects are replaced by one set of instructions. We are going to build this entire 3x3 system in under 6 minutes using logic that automates the placement and the coloring. The process follows a strict formula. We take simple input geometry, apply node logic to define the behavior, and Blender generates the final result. To start, select the Geometry node tab at the top of the Blender interface. This workspace changes how you interact with the model. Instead of manipulating vertices by hand, you are now writing the rules that determine where those vertices exist. We need to start from 0. Delete the default group input node to clear the graph. Now, add a cube mesh primitive. This node will act as the mathematical boundary for the entire puzzle. We need to divide this volume into segments. Set the vertices for X, Y, and Z all to 3. This creates a 3x3 internal grid. Switch your viewport to wireframe mode. You can now see the internal intersections created by those vertex settings. This grid is the scaffolding. It provides 27 precise coordinate points where we will eventually anchor our individual puzzle pieces. Now to place object at those coordinates, add an instance on point node. Connect the scaffolding cube to the point's input. Now we define the puzzle piece itself. Add a second cube primitive node and set its size to 0.49. That small offset creates the physical gaps between the blocks. Connect the smaller cube to the instance socket. The viewport now shows a solid 3x3 block. By using this setup, Blender is rendering 27 cubes using the memory footprint of just one master object. The scaffolding node handles the 3D placement, while the instance node provides the actual geometry. This keeps the file lightweight, even as the complexity increases. For the puzzle to be functional, the layer must be able to rotate independently. By default, if you try to rotate these instances, they will orbit the center of the entire grid like planets around a sun. To keep them in place, add a rotate instance node and enable the local space checkbox. Local space ensures that each cubelet spins entirely on its own center point, preserving the structure of the puzzle during animation. To paint the cube, we have to identify the 6 faces of every cubelet. Blender assigns each face a hidden ID number called an index ranging from 0 to 5. Open the Viewport Overlays menu and enable attribute text to see these IDs on the model. We can visualize this data by connecting an index node through a mesh to points node and plugging it into a viewer. In the front view, you can see the numbers mapping to the points. These numbers tell us which faces are currently pointing towards the camera. Switching to side view reveals indices 1 and 3. By isolating these specific IDs, we can write rules that only apply color to the faces pointing in a specific direction. The data shows that indices 0 and 2 align with the z-axis, 1 and 3 with the y-axis, and 4 and 5 with the x-axis. This gives us a logic-based map for the materials. We isolate these faces using 6 compare nodes. By checking if a face index equals a specific number, we can select one side of every cubelet across the entire puzzle. We then use a store named attribute node to save these 6 directional selections so that they can be recognized by the shader editor. In the shader editor, An attribute node retrieves the directional data and plugs it into the material's color input. Now, when we assign red to the x-axis faces and blue to the y-axis faces, the puzzle paints itself. The logic ensures that only the outward facing surfaces receives the 6 standard colors. This is the final result. A pristine, fully colored 3x3 puzzle generated entirely by rules. Because the coloring and spacing logic is based on directions rather than specific blocks. You can increase the vertex count on your scaffolding node. The 3x3 cube instantly expands into a 4x4 or 5x5, and every rule we have written remains perfectly valid. Every step in this process is now a reusable parameter. You can now generate any size puzzle or adjust the gaps by changing a single value in the modifier. Catch up with us to experiment with more procedural systems.